Very simple video on complete combustion of alkanes, which is this one. So I'll only be tackling this one and not this one because this is slightly more complicated and is not very well. This is the realistic combustion of alkanes or any other hydrocarbon fuels, but we'll just tackle the idealistic molar molar reality of this equation. So we'll tackle this one, and we'll go through the first around about 7 to 10 of these alkanes and discuss their combustion. So alkanes, as we know, are usually this has a group, but if it doesn't have a group, R prime, R prime is different. So otherwise, if there's no R group, then it'll be CN2N plus 2. All right, let's get started. The first equation is a sample equation of C2. This is this one, and so an alkane. This is what an alkane looks like. Sorry, hang on. Yeah, this is what an alkane looks like. Alkane is C2H2N plus 2. So if it's 1, it'll be 4. If it's 2, it'll be 6. If it's 3, it'll be 8. If it's 4, it'll be 10. If it's 5, it'll be 12. If it's 6, it'll be 14. 2 and plus 2. So 2 into 6 plus 2, that's 14. If it's 7, then it'll be 16. So the first one is known as methane. Second is ethane. And then propane, butane, pentane, hexane, heptane. And this is the ball and stick model of ethane. And the green here represents hydrogen atoms. And this is the tetrahedral shape of methane. And that's propane. Okay, so the complete combustion is a process where all of the oxygen consumes all of the hydrocarbon and produces carbon dioxide and water vapor. It's aerobic. There's no soot. There's no smoke. There's no carbon monoxide. There's no soot. There's no carbon deposits, carbon residue, and there's no unburned fuel. There's no unburnt fuel either. It's ideal. It's unrealistic, almost impossible, and is governed by the laws of thermodynamics, Hess's law, Born-Haber cycle, and as usual, we use stoichiometry, and it's calculational proportionation to determine quantitative relationships between reactants and products. So we use stoichiometry and its calculational proportionation to determine qualitative relationships between the reactants and products. So reactant 1 plus reactant 2 gives you via dynamic irreversible equilibrium product 1 and product 2. product 1 and product 2. So reactant 1 and 2 react to give you product 1 and product 2. And there's a Gibbs free energy change. There is entropy change, which is governed by Arrhenius law. Right, so this is how, I mean, we've got the first 4 hydrocarbons of the alkane series, and so we'll start balancing the equations. Molar ratios, according to molar ratios. Okay, so the first equation would be, so we've got 1 carbon, carbon's balanced, we've got 3 oxygen here and 2 here, and 4 hydrogen here and 2 hydrogen here. We'll start off by balancing the hydrogen, and the rest will fall in place. So that's 2 and 2, 4, so that'll be 2. So that's 1 mole of methane gas reacting with 2 moles of oxygen gas to give you 1 mole of hydrogen gas and 2 moles of water vapor. Methane and oxygen and carbon dioxide and water. So now the oxygen is 4 on this side and 4 on this side. 2 and 2, and then hydrogen is 4 and 4 on this side. Carbon is 1 and 1 on this side. So it's balanced. Now we'll move on to the second one, which is, so we'll start off by balancing the carbons, then we'll balance this, and then we'll put the resultant number here. So that's 3 oxygens, and that's 4 oxygens, so that's 7, so that's 3.5. So now we can see we've got 7 oxygen, 6 hydrogen, and 2 carbons. This one would be 4. Carbon is 3. Hydrogen would be 8. 4 and 6, 10, so that'll be 5. So we can see a pattern here. It's increasing by 1.5. So if I use 6.5 here, I'll see what I can get quid pro quo. It's 5, and that's 13. Yep, it balances. No, that's, yeah, 10, and then oxygen is 5 and 8, 13, and then this is the method I've always used. CHO, line it up, and then that's how you. So these are the first 4. For that, it would be so 12 carbon, 12 hydrogen here, and 5 carbons here, and then 5 and 2, 10, 6 and 16, so that's 16, so we'll have to put in I have to put in it. Now, for equations like these, where I'm using 3.5 and 6.5, what you can do is you can simply double it up. It'll be 2 moles of this, 13 moles of this, 8 moles of this, and 10 moles of this. So 2, 13, 8, and 10. But you don't have to. Back in the day, they would accept 6.5, but now they want you to round it up to integers, because obviously you can't have 6.5. Well, you can have 6.5 moles because of Avogadro particulate approximation. Right, so for this one, it'll be 9.5. Formula 9.5, and I can verify that. That's so. And then oxygen would be 6 and 12 and 19 divided by 19.5, so that's 90. That's that. So these are the first 6. So I've got heptane here. Heptane and 7, so I've multiplied it, put the 7 here, and I've put the 8 here. Now I've got 7 carbon. I've got hydrogen, which is 16, and then I've got oxygen, which is 14 and 22, so that'll be 11. Okay, so I've got the octane here. Octane is a very important field. Now, if I use my methodology of 1.5 increment from 7 all the way, throughout the alkane chain. So if this was 11, heptane was 11, and octane would be 13.5, 12.5. Sorry. This would be 14, and this would be 15.5. 15.5. Now let me verify that the approximation carries on. Approximation should carry on. So we have we get 8 carbons and 9 so we get 18 hydrogen, eight carbon, and we get 25 oxygen. So we get 25 oxygen. So 25 divided by 2, 2 will be 12.5. So with that we put 12.5. It is consistent from 11, the rise of 1.5, from 11 to 12.5. Then we move on to oh yeah, please remember that the left-hand side of the number of moles, the number of atoms on the left-hand side must always be equal to the number of atoms of each element on the right-hand side, which means that the right-hand side should be equal to left-hand side at all times. Okay, so this one would be 9, and then that would be 10. So that'll be 20. And oxygen would be 9 to 18, 18 and 10, 28. So that'll be 28. So that's consistent again. 28 divided by 2 is 14. This one should be 15.5, and we'll see now. 10, and that'll be 11. So we've got carbon sorted. hydrogen sorted, and oxygen is 20 and 31, so that's 15.5 again, so that's verified. Carbon, hydrogen, so right hand side equals left hand side, and so there is atomic homogeneity. That's brilliant, fantastic. And so this is how equations are. Alkanes increase by an order of 1.5, so the delta increase is plus 1.5 oxygen. So 1.5 moles of oxygen is required at every extra 1.5 moles of oxygen is required to combust the next member of the alkane series higher up in the series. The conclusions are that it's entertaining to write down and balance the equations of alkanes for complete and incomplete combustion. We haven't done incomplete, we'll do that later. It's simple, it's easy, it's schemed, and it enhances your understanding of stoichiometric proportionation. It is good practice of balancing equations. Useful as a brain game. So these are one of the many advantages of playing with equations for alkanes, alkenes, alkynes, and so it's as you can see, it's entertaining, simple, easy schemed. It enhances your understanding of the stoichiometric proportionation of how moles interact in terms of the molality, volume, room temperature, pressure, standard temperature, pressure, ideal gas situation, ideal situations versus real situations. It's a good practice in balancing equations, and it's useful as a brain game. It's very, very useful. Thank you very much. It was nice to tackle alkanes and their complete combustion, and I hope you learned something today. And if you have any questions, please post them below, and I'll try my best to answer them. Thank you very much. Take care. Bye now.